Aye, so I wanted to kind of continue with some of our mind your language stuff that we did quite a long time ago. You know, the word level and you know, how these terms are redefined in a mathematical way, which you can call sophistry, right? I mean, whether you go as far as to say it's deceit and stuff is something different, but put it this way, people have redefined those terms, those words, and they're redefining the use of our common language to make it appear to be something else. Yeah. And I'm saying appear because that's the word I want to look into.
Yeah. Sorry, can I just say, sorry, mate, just before you go, I mean, that's exactly the point. You know, if people are getting involved in their education and they're understanding these definitions and applying it to the way they're being taught, again, they're not actively lying. They're just not understanding the subtlety of the language, and you know, they're applying it in the right way in regards to what they're being taught. So again, it's just this whole aspect that people would have to be actively lying, and it's not the case. So, you know, people involved in mathematics, they're understanding these definitions, they're agreeing to it, they're practically applying it to their equations and whatever else they're up to, and it's working for them in the language of mathematics. So it's not that they're actively lying in order to apply it to a big deception. You know?
Spot on, man. You know, as I say, I think that's where half the trouble is, that people don't have those skills in words and rhetoric. And grammar and logic. We've talked about this often enough, and that includes mathematicians and physicists. You know, they are not immune to that, to the fact that they haven't had that upbringing either. So that they're just as easily fucked over, let's call it, you know, by these abuse of words, and language. Yeah, I was in the position myself. So what I want to look at today is the word called apparent. Now you'll see this word cropping up in so many different pieces of text, right? And basically, I'm talking about the words like appear, to disappear, appearance, and apparition. They all kind of, you know, are part of the same root, or the same word, and you have to differentiate very carefully of the meaning of that word in the different contexts in that it's being used. Yeah. So there's examples of it being its own opposite, right? There's definitions in mathematics. There's definitions when we're talking descriptively about apparent motion. You know, we're told that it appears to move, right? But it's not the stars and the sun that are moving above us. We are actually moving, right? So in that respect, it's made out to be something deceptive or unclear, right? But there's also the use of the word, for example, when I say it's apparent to everyone, then it means it's absolutely evident and observable to everybody. Yeah. And if I look at some of the definitions from Wikipedia, so I've just taken a screenshot, then there's two definitions that they give there. And, you know, when you look at them closely, they would appear to be absolutely contradicting each other, right? So we have the word apparent, meaning clearly visible or understood, and absolutely obvious, evident, plain, manifest, visible, discernible, perceptible. And then at the bottom, we've got it meaning seemingly, superficial, supposed, assumed, declared, pretended, feigned, right? So there's one word that is exactly its own contradictory in terms of its definition, right?
Yeah.
Now, there you go.
No, I was just going to say, you know, apparently, you know, Gav picks his nose and eats it. You know, I've heard that through the grapevine. So that's apparently, you pick your nose and eat it, Gav. But what would be apparent would be if Gav was on camera right now actually picking his nose and eating it, and then everybody would be able to see that that's exactly what Gav does. You know? One is hearsay and utter bullshit, and one is self-evident, apparent.
Yes. Everybody's doing it, picking their nose. And
sorry.
No, absolutely. No, I think it's just clear. So there's one word that has two different meanings, right? And here's another from another online website, right? Just to show people that I haven't cherry-picked anything, right? It was increasingly apparent, yeah? Or it means seeming to exist or to be true, right? But now I'm just going to go to the mathematical definition of what apparent actually means. And if you look up something like apparent angle subtended at the eye, then you'll get a whole lot of things around visual angles. And visual angles are then basically what it is when you look at something. So if you look at something and you try to define the separation between two stars in the sky, let's say, yeah, then you will automatically, from the way that you are built and the eye that you have, you will notice a visible separation between the two. And that separation between two objects would be your visual angle, yeah?
Yeah.
Now, I'm not going to go into this in too much detail, but the very fact that the visual angle is meant to be something that is apparent is also something that if you look into these Wikipedia definitions, you'll see that they specifically bring up the point about terminological confusions, right? So in astronomy, the term apparent size refers to the actual angle or the angular diameter, right? But if you look at things like experimental psychology, then apparent is something that is a subjective thing, yeah?
Yeah.
So we basically have those different meanings of the one word. Apparent can be obvious. It can also at the same time mean only seemingly or, you know, unclear. And from a purely mathematical definition, what it actually means is the angle subtended at the eye, the visual angle seen by an astronomical instrument or by your own eye, yeah? That is what the word apparent means, yeah? And then if you start to look into a whole bunch of different subjects, whether it's astronomy, optics, mechanics, vision, psychology, you'll see that word apparent being used in many different contexts, yeah? And the word is very ambiguous in a lot of cases. I would contend that it's also nefariously used, deliberately used, right?
Yeah.
To bring about these contradictory things or to have this dissonance that comes with people believing things that shouldn't be believing in. So, you know, an example would be the ecliptic, where the sun appears to move with respect to the fixed stars, yeah? As seen from the orbiting Earth, the little picture on the right-hand side, or the sun's apparent motion against the background of the fixed stars. Now, looking at that one sentence, you could either think, okay, the sun appears to move, but it's not. It's us that's spinning. That's one interpretation of it, right?
Yep.
That's what they like to tell us, yeah? You can also think, though, that the sun's apparent motion is exactly that. The visual angle measured during the course of a day as the sun goes across your observational visual field, yeah? And that apparent angle is really a mathematical term that defines also some of the things that I want to get into in a second, namely spherical astronomy. Yeah. So what I'm trying to point out is that these words, you have to discern very carefully how they're being used and where they're being used and what their actual meaning is. Most people will think, oh yeah, apparently, yeah, it only looks that way that the sun's moving. It's us that's rotating, yeah, or spinning on our axis, or it's us that's going around the sun once a year that is causing the sun to appear to move, yeah? But mathematically, all we're doing is measuring the visual angle of the sun as it moves through the day. And as we all know, and our common senses tell us, we ain't fucking spinning. This place is stationary and fixed. And yes, the stuff is moving above us. How it's doing it, I'm not sure. I'm not going to speculate. But what I do know is that the pish they're telling me that I'm spinning is totally nonsense. And these words are being used to confuse me, yeah, or confuse us, yeah. So I'm just going to take away this one and go to this book called A Manual of Spherical and Practical Astronomy, right? Can you see that still, eh?
Aye.
Right, okay. Now, before people get worried that I'm actually going to go through this 700-page book, I'm not. What I want to show is that by looking at the abstract and the preface and the introduction of these books, you can actually spot the sophistry without being a mathematician, right? And that's what, you know, if I look at a book, then if you don't look at the mathematics in the equations, because where the sophistry is right at the start in the first principles, the axioms, the assumptions of what they're trying to do. And there's some good examples in this that I'd just like to step through, yeah? It's only a couple of pages, so bear with me, yeah? So this is a book written in 1863, so quite a long time ago. Yeah, 100 and what is that? 1963, 150 years ago. Yeah, and by a professor of mathematics and astronomy at Washington University, St. Louis. Right now, this book, if I just look at some of the chapter, let's say the index, it should be coming in a second, which I just want to flip to. Here it is here. So if you guys just have a quick butchers at some of the contents here, right, of spherical astronomy, you'll see it has a lot to do with the celestial sphere. So that's the big dome-like structure that we see when we look out at the night sky. It has to do with the ephemeris, yeah, which is all these big star catalogs, yeah, where people, you know, have catalogued and tabulated the movements of the little luminaries in the sky, yeah, and on the basis of tabulating them over a long period of time, they can make predictions. It's got nothing to do with the mathematics. I'll say it again, just for people. If you look at something close enough and you record it over hundreds of years, then yes, you will be able to predict when something comes again, right? Because it keeps reoccurring. Right? It's a periodic thing. I know when the eclipse is coming, not because I have a mathematical formula that proves it in any way, but because I know from looking at it long enough that it's going to repeat itself. Yeah? That is a star catalog, right? Clear and simple. Then there's all kinds of tough talk here about the figure and the dimensions of the Earth and the reduction of observations to the center of the Earth. I'm going to come back to that because it's quite an important part. But this book would probably have been used by anybody in the 1850s who was going to sea. When I say sea, I mean ocean, traveling the world's ocean, you know, ruling the 7 seas of Britannia and all that pish, right? To do that, you would have had to had knowledge of spherical astronomy and of trigonometry to be able to find your position on the sea, right? And you would have done that by astronomical observations, yeah? And there's a whole bunch of stuff in this book of how to do that. You can see here by the pole star, for example, everybody knows if you measure the altitude of the pole star, then it tells you what your latitude is, right? On a supposed sphere, yeah? So all these chapters will help people navigate around the world, right? And there's a whole bunch of stuff, right? Finding your longitude by all kinds of ways, finding your place at sea, meridian lines, and this is quite an extensive, you know, dictionary. It's more of a reference work. But if you were seriously looking to navigate around the world across the sea, you would need to have some of these tools here, right? Now, I'm just going to skip to basically the first couple of pages because I think this is really important that people understand this, right? So, spherical astronomy, what the fuck is it? Let's just look at this first paragraph. From whatever point of space an observer be supposed to view the heavenly bodies, they will appear to him as if situated upon the surface of a sphere of which his eye is the center. If, without changing his position, he directs his eyes successively to the several bodies, he may learn their relative directions, but cannot determine either their distance from himself or from each other. A really important point. Spherical astronomy only has to do with direction, nothing else. It's the position of something when you look at it in a supposed celestial sphere, and you're looking at its position on the sphere. Yeah. Now, I don't believe in the word heavenly bodies. I've got no reason at the moment to assume that they're bodies. I've never been. They can tell me a lot of stuff, but I don't know whether the sun is a body or not. Yeah. What they do in this second paragraph then, though, is and I would agree wholeheartedly with this first paragraph without the word bodies, that yes, that is the way I see things. And yes, from a purely geometrical perspective, I cannot tell if something is far away and is really small, sorry, really big, or whether it's close to me and really small. If I hold a penny in front of my eye about whatever arm's length away, it will be the same size as the sun in the sky. Yep. So what is it? Is the thing close, or is it far away and really big? It is impossible to tell geometrically. Yep. Yeah? Yep. And that's why that first paragraph, as far as I'm concerned, is correct. The second paragraph, they start to talk then about the position of an observer on the surface of the Earth is constantly changing. Now, this is obviously where I don't agree. In consequence, the diurnal motion, or the rotation of the Earth on its axis. So that's where they're trying to tell us, okay, we are spinning, yeah? And that's why the stars appear to move. Now, the only other option to that is, no, we're not fucking spinning, and it is the stars that are moving, yeah? This guy's taking the stance that, yes, he's on the surface of the Earth, and because it's spinning and because it's going around the sun, his position is changing, so he's going to see things differently. Yeah? And he goes on to say that the changes produced by the diurnal motion in the apparent, there's that lovely word again, relative positions or directions of the heavenly bodies are different for observers in different parts of the Earth, and can be subjected to computation only by introducing the elements of the observer's position, such as latitude and longitude. So that's where, mathematics would have us believe that we're on a sphere, we're on the surface, and we can pinpoint our position on that sphere through two coordinates, namely latitude and longitude. And I'll get to that in a second as well, because it's quite interesting the way it's shown in this book. Let me just go through the paragraph though. But the changes resulting from the annual motion of the Earth, as well as from the proper motions of the celestial bodies, may be separately considered. Very important phrase, because you can separate the geometry of position from the geometry of motion and time, which is exactly what they've done. Mathematics concerns itself nowadays with the geometry, and physics concerns itself with motion. And because these two things have been separated, physicists don't necessarily know geometry. You probably won't find a physicist alive today who would understand this book, yeah, or be able to really go through the theory of what the mathematicians meant. I may be generalizing, there probably are a few physicists, but you get my point. Yeah. Because they've separately considered these things, and the directions of all the known celestial bodies as they would be seen from the center of the Earth, again, very important, from the center of the Earth at any given time, may be computed according to the laws which have been found to govern the motion of these bodies from data furnished by a long series of observations. Exactly what I was saying a second ago, because you tabulate things over a long period of time, yeah, then that's where the data's coming from, that people show what these motions of these bodies or of these luminaries are. I'd rather refer to them as luminaries, I think. So that it's got nothing to do with the mathematics behind it. Where this is coming from is tabulation of looking at things for a long time. Yeah. And here's a very clear separation. The complete investigation of these changes belongs to physical astronomy, and that's where they would consider distance and magnitudes as well as the direction. But spherical astronomy treats specially of the directions of the heavenly bodies. And in this branch, therefore, these bodies are at any given instant regarded as situated upon the surface of a sphere of an indefinite radius described about an assumed center, right? So there's a very clear separation of the geometry of spherical astronomy, which is talking about spheres, position on spheres, and physical astronomy, where they're trying to tell us what the actual distance and the magnitude and how big these things are, yeah? So very clear separation. And you've heard me saying this before, and I don't want to, well, I will labor the point because it's important, is that a sphere is not the same as a ball. Yeah. A mathematical sphere is a two-dimensional geometry that is not the same as a three-dimensional physical ball. Yeah. Spherical geometry is done nothing else other than redefine straight lines to be great circles on a curve, right? Curved segments. and a redefinition of what parallel means, but it is still a two-dimensional geometry, and you can go from planar geometry to spherical geometry with the swap of these two definitions, and nothing else will change. Your equations will stay the same. You can transform between one and the other without losing any data or integrity. Spherical geometry is the same as planar geometry. So, and I just want to stop there and labor that point a little bit, because I see people still confusing this issue, saying, oh, but we navigated the world. That's only possible if the mathematics was correct, and it really is a ball.
Yeah.
No, it's correct because the mathematics of a sphere are two-dimensional mathematics, yeah? And not because it means that we're on some three-dimensional ball floating in a vacuum, right? And anybody who wants to deny that, I urge them, just look at a few of the books, go back in time, pull these things up. You can even look in Wikipedia. They've got a very clear differentiation between what's a two-sphere and what's a three-ball. The fact that you can navigate around the world has everything to do with spherical mathematics. That's an absolute given, but it doesn't mean we're on a ball, right? Yeah. And any mathematician will confirm what I'm saying, right? So all the globe people out there who still believe that mathematics is proof, you really want to go away and have another look at it, yeah? So I just want to, there's just one paragraph and a footnote that I want to go through, and then I'll relieve you guys from this murder of mathematics. But I just want to make sure that people understand what a spherical coordinate is. So the direction of a point, so any point in, in our physical space, right, can maybe expressed by the angles which a line drawn to it from the center of the sphere, or point of observation makes with certain fixed lines of reference. Now, this is a really sneaky bit coming up now, but since such angles are directly measured by arcs on the surface of the sphere, the simplest method is to assign the position in which the point appears when projected upon the surface of the sphere. Now, I don't know whether this is complicated, so I've got a little video that I hope will help.
Yep.
Which is something I did here quite a while ago in a program called GeoGebra. I'm just going to scale it back. So I want people to understand what it means. There's a sphere. There's 0 is the center of that sphere. And I've drawn a spherical triangle on here with A, B, and C, right? So 3 arbitrary points. Now, if I look at exactly those points, you can see that if I cut that sphere with a plane, then that plane goes through the arc segment BC, right?
Yeah.
And if I do this with some of the other ones, that one, I have now drawn a plane going through the center of the sphere that is cutting through the points O, A, and C. And the arc segment CA is now part of that circle that is being left behind by those planes. So I'm just going to move this video forward a little bit so that it can become a little bit clearer. I'm going to put the circles on there. So these are the great circles that you can see. And I can change some of the coordinates on that sphere. For example, I can move A or I can move B up and down, yeah? And you can see that the measure, this arc, the arc BC and the arc CA down at the bottom are actually exactly the same as the angles that are being subtended at the center of this origin, right? Yeah. So that whatever, if I make those angles bigger, it really is the same geometry as this spherical wedge, right?
Yeah.
And that's where the trickery comes in. So if this was a real object, like an axe, let's say, an axe head, then the angles subtended at the point O by each one of those lines, OB or OA or OC, any of the angles in between them can also be measured by the arc lengths of the great circle segments. Yeah?
Yeah.
So that's the connection between the two-dimensional spherical mass and the three-dimensional ball mass. The angle that I measure at the center of that sphere, if it was a real planar angle by a wedge, something that looks like an axe head, it's exactly the same as if I measure the lengths of these arcs on the sphere. And that's why it was so useful at navigation, right? Because what you were seeing can then be measured basically using spherical geometry, and all the problems that you had in navigation were basically reduced to solving this triangle. If you knew one angle, then you could get the other side, so you could find out what the length was, or if you knew three lengths, you could get the angles. So basically, if you're navigating anywhere, then what you're doing is trying to solve a spherical triangle. And the sneaky bit is that this spherical triangle is measured using arc lengths of a sphere, but it's the same geometry that you would have on a 3-ball if you were measuring from the center of the sphere.
Yeah.
Now, I hope that's clear, and maybe people might want to revisit this afterwards and mull through what I'm trying to say. I know it might be, I don't know, too quick and a lot to take in at one point, but just to go back to what this piece of text said. So we're drawing a line from the center of a sphere or a point of observation, and we were using certain fixed lines of reference, and then came this sentence, but since such angles are directly measured by arcs on the surface of the sphere, the simplest method is to assign the position when projected upon the surface of the sphere. And that's exactly what I've shown there. I've basically shown that the angles at the center, right, from the lines drawn at the center, are actually measurable by the arcs on the surface of the sphere. So that's the 3-ball, in this case, from the center of a ball, if you like, looking out, is basically the same geometry as a 2-dimensional sphere where I'm using the arc lengths on the surface of the sphere. I just want to go through this last paragraph and then we're pretty much done. But so every single projection, so you hear a lot about this all the time, astrolabes that were used for navigation. There's all kinds of different quadrants. Everything that people have used is based on this idea of projecting from a sphere. And there's only really two ways to do this. You have basically what's called a primitive circle, and you have what are called secondaries. And basically that's what we would normally call the equator, for example. And secondaries would be these longitudinal lines, that you can see when you're looking at the globe model. So basically you have two spherical coordinates, with one is the distance of the point from the primitive circle, and the other one's the distance intercepted on the primitive between the secondary and some other one. And you have to assume what is the origin of the coordinates. I'm just going to draw I'm just going to show another little picture here. So just to make this clear to people. Here is, if you like, these two coordinates. So one coordinate is the length of this arc, which we would call altitude, up to where we can see a visible star. And the other one is from some reference point like north, where we say, okay, I turn to the right, let's say 45 degrees, and then I tilt my head backwards another 45 degrees, and that's where I'll find that star in that position. So this would be an example of a coordinate system based on that principle which was just shown. If I go back to it again, the principle is always the same. You suppose that you have some primitive circle, and then you refer to that circle by finding out where the secondary circles pass through it. Now, in physics, you can do all kinds of different coordinates. The one I just showed was the one called the altitude and the azimuth. And this is where I find it very interesting, this next. In this system, the primitive circle is the horizon, which is that great circle of the sphere whose plane touches the surface of the Earth at the observer. And there's a little asterisk here, which I'm going to go into. But what's interesting is this: the plane of the horizon may be conceived as that which sensibly coincides with the surface of a fluid at rest. Now, basically what they're saying there is that if you look at the big wide world of oceans and seas and large standing bodies of water, then yes, that can be conceived as your horizon if you look out towards it, i.e. water is fucking level, right? It's planar, yeah? And if you're standing looking at it, then it will in fact match your horizon. But one of the things that's really sneaky here, and I really want to point this out, even so that mathematicians can also see this. This little star here, where they're talking here about the circle of the sphere whose plane touches the surface of the Earth. I'm just going to go to this little asterisk at the bottom, and I'll just make this a little bit bigger. Oh, that's too big. So, in this definition of the horizon, we consider the plane tangent to the Earth's surface as sensibly coinciding with a parallel plane passed through the center.
Yeah.
Now, basically what they're saying is that if we consider the radius of the celestial sphere to be infinite, so really, really far away, in galaxies far, 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 far away, then the radius of the Earth can be taken to be 0, right?
Right.
So they're basically doing away with the whole idea of the radius of the Earth from the center point to the surface can be completely ignored in this definition of the horizon, right? Which is very convenient for them, of course, right? Because that way they can use the same projection of the sphere from the center of the eye to be able to use their sophistry. Yeah. And it's very similar to the same fallacy we see everywhere else, Dale, that, you know, that they assume light rays to be so far away that they're parallel when they come in. They're basically using the same trick here in mathematics to redefine where the horizon is and to completely ignore the theoretical radius of the Earth. Yeah. They're basically saying we can forget it because it's so small as compared to how far away the celestial sphere is, that we don't need to worry about it anymore. Yeah. In general, any number of parallel planes at a finite distance may be regarded as marking out upon the infinite sphere the same great circle. So it doesn't matter whether I'm using a plane on the surface, like a tangent plane on the surface, or a plane cutting through the center, or any other plane in between. They're basically saying that they can all be considered as one and the same thing, right? Yep. Because we're in spherical geometry, we're only looking at direction. So that is, all parallel lines or planes must be regarded as intersecting the surface of the sphere in the same point or the same great circle. Because everything's so far away, they're all going to meet at the same point. Yeah. And again, the fallacy is believing that everything is so far away, right? It's the same fallacy we see again and again. The point of the surface of the sphere in which a number of parallel lines are conceived to meet is called the vanishing point. Oh, what a coincidence. Yeah. That perspective and vanishing points is so deeply ingrained in the terminology of spherical astronomy, right? Yeah. And the point of the surface is conceived to meet the vanishing point, and in like manner, the great circle in which a number of parallel planes are conceived to meet may be called the vanishing circle. So if I was to go back to thinking of the hula hoop that I have round my eyes when I'm looking at something, right? I can rotate 360 degrees. I can see a flat horizon. If I rotate on my, do an about turn, so to speak, then that is what they're referring to as the vanishing circle. And the vanishing point, they're basically doing away with the radius of the Earth so that they can use the celestial sphere, which is two-dimensional spherical geometry, to navigate around the world based on tabulated positions of stars. Yeah. And it's very, for me, this is very telling. You see perspective involved in here. you can see how they're confusing the definition of what horizon and what these terms, these coordinates are, and you can transfer between the two. And that's all that they're doing when they're doing this, how should I say, mathematical sophistry and telling people it has to be a sphere because we've navigated the world back and forth, right? And so, I just want to make clear that if you look very carefully at the words being used, don't even go into the mathematics. So don't bother about all the stuff that comes. Just look at what their assumptions are and question them. That's what I'm trying to make people aware of.
Excellent.
So I hope that wasn't too long-winded, my man.
No, I'm still, I mean, you know, same as everybody else, so the majority watching this, mate, you know, I've still got a lot to learn in regards to this. So again, it's invaluable to me, you know, that you've got that knowledge and you can share it. I'm starting to piece wee bits together with it. So, your questions I would have, I mean, when they're saying this, you can do away with this. If you're trying to navigate and you have to negate the radius of the sphere, so again, you know, you're just assuming level, you're just assuming a plane. But what I'm kind of getting for that, does that then suggest, you know, because I've heard this said a number of times that, or does it, I'm asking you, does it point, or am I missing the point altogether? Does it point to the possibility that what we see as the stars and the luminaries are different to each subject depending on where you are? Like, you know, they're somehow aligned with your specific position, and it moves relative to where you are. I mean, I don't know if I'm way off the mark with that. I don't know if it's even pointing towards that, but do you understand what I mean?
Yeah, I do understand what you mean. So, I mean, what they try and tell us is that by looking at the stars, we can locate exactly where we are on this supposed sphere that we're living on, right? Yeah. That's what they're trying to tell us, right? So by looking at the stars, by cataloging, by making those observations, we can basically make one field observation, which we measure with our physical, you know, instruments, and we find the separation. And then we can go away and look at a catalog of tabulated catalogs. And if we know the instant at which something is being measured, i.e. if we know the time it's being measured, then we can use the two of those things, the field observation and the star catalog, and to bring it together and to pinpoint our position on a supposed sphere. That's one way of looking at everything. The other way of looking at it is what we've said, you know, multiple times. If I walk around something, then I'm going to see things at different positions all the time. If I'm in Scotland, I'm going to see different stars than I will if I'm in Spain, right? Yeah. Just because of the very fact that, yes, I am in a different position, but because of the way things appear to me, right? And again, we're back to the angle that I'm measuring. It doesn't mean that the things curve, right? I could be on a flat plane looking at certain things, and I am basically seeing those things because of the way my eyes work and because of the position I'm in. The situation of my eye relative to these things is the other way of looking at it, and you're on a flat plane. So there's no reason. So they'll always jump to this, okay, it'll show you, we can use these measurements to show you where you are on a ball, if you're upside down or on the top. But the other way to look at it is you're on a flat plane, and just because I'm going away from you, then things will fall in your visual field, and I will appear to be lower than I was when I'm getting closer, right? So I think that's the question you were trying to ask, whether it has a certain meaning, or did I misunderstand what you were asking me?
No, you gave me a bit more clarity there. You know, I was just kind of waffling, trying to make sense of it. Again, it's not easy for me to grasp this. I've never had a background in any of this stuff. So, as I say, I just understood the language in an overview kind of sense, but the expertise level, I've not got a clue. So, I'm learning the same as the majority, mate, you know?
Well, I mean, I think that's what I'm trying to say, that, you know, if you look at the introduction, the preface, the table of contents, the assumptions that are generally at the beginning of any book, then I think that's the most important thing that people need to discern, to dismantle, or to desuffocate, right? This deception, because you won't find the mistakes in the mathematics afterwards. That's where, you know, hundreds of mathematicians will have pored over these equations and would have found any mistake in them. But where they don't pore over, what they don't look at closely enough, is the assumptions that are being made. Here we can see in this book, we're basically making the same assumption that we make all the time, that stuff is so far away that the radius of the Earth can be ignored. And it's the same fallacy as light rays are parallel because we know the sun is 1 billion miles away. And then use that, you know, for example, that Eratosthenes, right? The measuring of the stick. It's the same fallacy in geodesy. It's the same fallacy being used in astronomy. And those things all come back to the same mathematical sophistry at the end of the day, which is what I'm trying to point out. And I'd love a mathematician to come along, or even somebody who believes in the globe, who thinks he understands mathematics, to come along and discuss it. You know, let's rebut this stuff. Show me where I'm wrong. Show me where, you know, these assumptions are correct to be making. Yeah, because you can't make those assumptions, Del. Yeah, that's you already believing in the vacuum of space, and that, you know, you're making a base assumption. So it's circular reasoning, right? You can't say that mathematics reflects reality properly, because they're making assumptions that are not observable and not directly within our direct experience. Yeah.
Spot on, mate. Right. I mean, even just looking at some of the diagrams that they use, you always see that, you know, it's a planar surface and measuring angles. I spoke to this about the other day, the whole, you know, the Masonic compass and square and what that actually is representing. You know, the squares for Earth and the compasses for, just as you point out, for, thank you, pinpoint the location and astronomical movements. Am I right? Is that right?
Yep, absolutely. Yep.
So, you know, even just in a simple term, looking at the diagrams and how these things work, it's assuming a plane, and then you're measuring the angle from your position to where these things are, you know?
Yep. Yeah, I mean, you can see it all the time, and there's lots of documents and books and manuals about, you know, whether it's how to fly, you know, where they're assuming that it's a plane level surface, and there's this interchangeability between heliocentrism and geocentrism, which physicists agree you cannot tell the difference, right? Both of these things are equally, you know, how should I say, equally true, if you like, because there's no way to be able to tell the difference from a mathematical standpoint. Yes, from a physical standpoint, we can sit here quite clearly and say, I ain't fucking spinning, right? And I know I'm not spinning because I trust my senses. But from a mathematical perspective, you couldn't tell the difference between looking at it one way or looking at it the other way, right? And that's, but mathematics proves nothing. And I don't weary in trying to make sure that people understand that. I see one guy, and I'll mention him specifically, Wolfie6020. He's got a little video competition. He's trying to do a search and rescue mission, and he's basically challenging flat earthers to come up with a flat Earth map that would allow them to find somebody at sea, right? Along the lines of, haha, the flat earthers don't have a map. The globe map, or the globe sphere, we can pinpoint people at sea and rescue them. So again, we must be right. It's a ball, right? But if people understand what I'm trying to say, I can switch between his spherical version and the planar version with a very simple transformation. It's not even difficult. There's a couple of sines and cosines in there, right, that look scary, but there's actually no difference. So whatever spherical solution he finds to this challenge, right, and somebody says, this is my map, I'll just say, take this mathematical transformation, change it into planar coordinates, yeah, and hey, that's my flat Earth map. And you know what? It'll find the person exactly the same as he can, because the mathematics is no fucking different, yeah? So, you know, again, you know, I'm pointing to that guy's channel because he tried it a year ago, you know, putting out this red herring of trying to get people to make a flat Earth map, whereas the reality of the situation is you don't need to redo the mathematics. It's already there. I've said this before. You know, what they use to prove their spherical globe bullshit, we can use exactly the same mathematics if we slightly redefine the terms and the axioms, and they work just as well for us too, right? So there is no dichotomy. Yeah?
Which is probably where they originated in the first place, and the spherical nonsense came later. You know, because they keep invoking this fallacy that all these ancients and people back then, you know, assumed a globe. Well, you know, that's a fallacy in itself. If I look at the instrumentations and the methods they used, you know, they weren't assuming a globe. So whatever's happened along the road, they've twisted the planar understanding and how things were applied, and then, you know, twisted the mathematics to suit their concept or idea of a sphere.
That's exactly what they've done. Yep, exactly what they've done. They remodel it now. Even this whole geodetic, you know, sciences, where they're trying to get us to believe that it's all, you know, being measured by satellites in space. You know, all they're really doing there is also just reworking data and observations they had, making a model, and now they're trying to get us to believe that model, right? Yeah. But it's got nothing to do with that. It's just mathematical sophistry and tabulated observations and real planar surveying where markers were put in the ground and things were measured properly. You know, even that whole science is using the same fallacy to try and deceive us that there's something up there that's actually measuring stuff. It's bull crap, absolute bullshit. I can see it so clearly, right? I just wish I could sort of beam it into everybody's head, you know, immediately, you know, how the mathematics has been duped, you know, and it, well, I don't know what to say.
I'm trying. I wish
trying to bring it simpler and simpler. I know it's maybe not trivial, but
no, well, it is. It's just because it's your line of expertise, you know, and I wish you could just beam it right into my skull. Be much easier, but I'm going to do my best to keep pushing and try and understand it as much as I can to whatever level I can get to, you know. I think it's important for other people to try and understand it as well. But, you know, appreciate that there's people like you there that are willing to share their knowledge and tear apart these things, mate. You know, it's invaluable. People like me, to be honest with you.
Well, I mean, as I say, I don't think it's difficult as long as people don't get too lost or too afraid of the mathematics. Just look at the text, the assumptions that they're making, and you can pull a lot of these books. So I've got at least 50 of those books, right? They used to write them, you know, I mean, because it was such an important thing back in them days, 150 years ago. The libraries are flooded with those books, right? How to do spherical, how to use the instruments properly to navigate. And they've all got the same underlying flaws in their assumptions and in their conceptions. And again, I'm not saying the mathematician has done it to deceive us. I'm just saying that he's basically redefining terms and words, right? Yeah. He believes them to be true, maybe because he had that education. And what we need to do is reclaim those words and look at them very closely and say, no, hold on. You can't just ignore something like that, or you can't just make that assumption, or you can't just redefine that word to suit your own purpose, right? Yeah. You have to look at these things, you know, the real first principles of them, and that's where the fallacies lie. And that's where I think the discernment and the empowerment will come. Doesn't have to be mathematics, but in all these different, you know, levels of discernment that we're trying to bring, yeah?
Yeah. So it was interesting, you know, just listening to or looking at the word in there when they were, you know, saying, you know, the projector assume the stars to be on the outside edge of a sphere, which, you know, if I play into my whole, you know, hypothesizing, you know, the possibilities that we are actually encased in a sphere would be, you know, even more.
It will work just as well.
So I've said that to people before. Well, you know, people talk about this in a conspiratorial type arena. You know, everything they tell you is reverse, right? So, you know, let's look at the heliocentric model then. You know, the stars and you know, these luminaries are infinitely far out in the vacuum of space. We're on the outside of a sphere, and everything's calculated to the centre. So, you know, you could reverse that and say, okay, well, the stars and these things are fixed on the outside shell of a sphere. We're on the plane within it, and at any moment given time, that's us. We're at the centre of that sphere, and that's where we're measuring for. So, you know,
that was basically the old model. The Ptolemaic system was basically a geocentric one that believed in those kind of shells, and that, you know, that's the way things moved around. You know, I mean, that is basically a geocentric view of the world, and it worked for thousands of years, right? You know, everybody thought that was just fine, yeah. So, yeah, absolutely. What I'm saying is the mathematics is a descriptive language that you can make your terms and definitions, as we've seen in this document, And depending on those terms and definitions, that also drives what your conclusions and the interpretation of your conclusions. So yes, we could make a descriptive mathematics tale that would show exactly, the mathematics would be fine, and it would be, you know, perfectly consistent within itself. And we could then claim just as easily, yes, the mathematics proves it's a flat earth. What I'm trying to say is mathematics cannot be used as a proof for either of them. That's where we come back to physical substances, direct experience, common sense, yeah, and those things, which would be the next topic, if you know what I mean, yeah?
Yeah.